Assalamualaikum warahmatullah and greetings everyone. In this video, I will explain on chapter 4 on Tests of Hypotheses, focusing on testing the single population variance sigma squared or population standard deviation sigma. Let's proceed to this topic's learning objectives in the next slide. This topic's learning objectives are listed as follows. At the end of learning this topic, you should be able to achieve the first learning objective, which is to perform a hypothesis test on a single population variance, sigma squared, or on a population standard deviation sigma, using the correct procedure step by step. The second objective is to identify the suitable test statistic and calculate its value correctly. Next, the third learning objective is you should be able to make a statistical decision correctly whether to reject the null hypothesis or not based on comparing the chosen and calculated test statistic value with the corresponding critical value. And finally, you should be able to provide a sound and practical conclusion about sigma squared or sigma that you have tested. You may refer to Statistics for Engineers textbook page 91, which discusses this topic in detail. You can also refer to other online references to help you gain a much better insight on this topic. The choices of hypothesis tests are listed in the following table. In this table, we look first at testing a single population variance, which is sigma squared. However, we can use exactly the same method and procedure for testing a single population standard deviation sigma. So back to the table here. The first choice of hypothesis test is a two-sided alternative hypothesis test when we want to test if there is any change or any difference in the value of population variance. Therefore, under H1, we have sigma squared is unequal to or different from a certain value, sigma naught squared. The choice of test statistic is the same as the choice of statistical score used in Chapter 3 on estimating a single population variance, that is, to use a chi-square score. In Chapter 4, we will use a chi-square test statistic and compare it with a chi-square critical value. Since we have a two-sided test as the first choice, the rejection rule is then reject H0 if chi-square test is less than the left-sided critical value, that is chi-square 1 minus alpha over 2 nu, or if the chi-square test is more than the right-sided critical value, which is chi-square alpha over 2 nu. Please note that the degrees of freedom denoted by nu here is the sample size n minus 1. In addition, both critical values are positive, even for the left-sided critical value, since chi-square values are strictly non-negative. So the chi-square values can never be negative, be it for the test statistic value or, more importantly, for the critical values. Next, the second choice of hypothesis test is a left-sided alternative hypothesis, where under H1 we have sigma squared is less than a hypothetical value, sigma naught squared. For this left-sided test under H0, we can either just write sigma squared equal to sigma naught squared, or sigma squared is at least sigma naught squared. You should notice that the statements under H0 must contradict with the statement under H1. The decision rule follows what we write under H1. For this second choice, the decision rule is reject H0 if chi-square test is less than the left critical value, which is chi-square 1 minus alpha nu. The last choice of hypothesis test is a right-sided alternative hypothesis where we have under H1 sigma squared is more than the value sigma naught squared. Here, under the null hypothesis, we can write either sigma squared is equal to sigma naught squared or sigma squared is at most sigma naught squared. The decision rule follows what we write under H1 though, that is, reject H0 if chi-square test is greater than the right-sided critical value, which is chi-square alpha nu. What is the chi-square test statistic that you have to calculate? The answer is the chi-square test is defined as the sample size n minus 1 multiplied by the sample variance s squared divided by the hypothetical value of population variance under H0, that is sigma naught squared. This formula is available in the statistical table booklet, page 3. If we look again at the table from the previous slide, suppose now we want to test a population standard deviation sigma instead of testing population variance sigma squared. Do we have to change anything, especially the test statistic and the critical values? For example, do we have to square root the test statistic and the critical values? The answer is certainly no. You do not square root the test statistic and the critical values when you test sigma. As I mentioned earlier, you can use exactly the same method and procedure for testing the population standard deviation sigma. You may only need to state the hypothesis statements on testing the population standard deviation sigma clearly like this. However, when you test sigma, you are actually testing sigma squared as well. For example, if you test sigma equal to 2, you are actually testing sigma squared equal to 4, right? If under H1 say sigma is greater than 2, you actually have under H1 sigma squared is greater than 4. Am I right? So other steps remain the same. It means the decision rules and the critical values are the same. Even the test statistics is defined in the same way as before. Please, you should neither square root the critical values nor should you square root the test statistic when you test a single population standard deviation sigma. In constructing the confidence interval for sigma in Chapter 3, that is different. In Chapter 3, you are talking about estimated values. Of course, you need to square root the estimated values for sigma squared to get the estimated values for sigma. However, in Chapter 4, we are talking about testing procedure. I repeat, testing procedure. What I'm saying is that the testing procedure for testing sigma is exactly the same as the testing procedure for testing sigma squared. Of course, for the conclusion, you need to conclude on the sigma if that is the parameter you want to test. Please look at example 4.3 on page 92. A drilling machine is used to drill metal plates in batteries. A random sample of 25 plates results in a sample variance of hole diameter of s squared equal to 1.82 mm squared. If the variance of hole diameter exceeds 1 mm squared, the drilling machine must be serviced. Is there evidence that the machine needs to be serviced? Use alpha equal to 0.01 and assume that the hole diameter has a normal distribution. As usual, identify or recognize the information provided in the question. Here we have the sample size n equal to 25. We also have the sample variance s squared given by 1.82 millimeters squared. What is the parameter of interest we want to test here? If you look at the question again, is there evidence that the machine needs to be serviced? The machine must be serviced or not depends on the variance of the hole diameter. Therefore, the parameter of interest here is obviously the population variance sigma squared. When we know it's the sigma squared that we want to test, then we know we have only one case, that is to use a chi-square test. Therefore, we can proceed running the test on sigma squared at the level of significance alpha equal to 0.01. How to write the null and alternative hypothesis? Remember the rule. Under the null hypothesis, we can write H0 sigma squared equal to 1 millimeter squared. What about H1? Look again at the question. If the variance of hole diameter exceeds 1 millimeter squared, the drilling machine must be serviced. The keyword exceed here refers to a greater than sign which should be under H1. Therefore, we can write under H1 sigma squared is greater than 1, which indicates that the drilling machine must be serviced. We can also write the null hypothesis H0 like this. Sigma squared is at most 1, which indicates that the drilling machine must not necessarily be serviced. Remember the rule. When you want to write the null hypothesis, any statement with equality sign must be under H0, and any statement without the equality sign should be under H1. Here the keyword exceed should be under H1. The complete solution is available in the next slide. Let's look at the complete solution for example 4.3. We already knew the null hypothesis and the alternative hypothesis from the previous slide. We also knew that we should use a chi-square test statistic in this example question. Now we can write the rejection rule. Reject H0 if chi-square test is greater than the right-sided critical value, which is chi-squared alpha nu, where alpha is 0.01 and the degrees of freedom nu is 25 minus 1, which is 24. The critical value chi-squared 0.0124 can be obtained from the statistical table booklet, page 36, which has a value of 42.9798. Next, calculate the chi-square test statistic, which is given by the sample size n, which is 25 minus 1, multiplied by the sample variance s squared given by 1.82, divided by the hypothetical value of sigma squared under H0, which is 1 millimeter squared. So the chi-square test value is 43.68. The next step is to make a decision. Here, the chi-square test, which is 43.68, is slightly larger than the critical value, 42.9798. Nonetheless, the test statistic value is already in the critical region. Hence, we can decide to reject the null hypothesis H0. Again, please do not stop here. You need to answer the question. Is there any evidence that the drilling machine must be serviced? When we reject H0, then we have evidence to support H1. In this example, then, we can conclude that we have evidence from the sample data that the variance of hole diameter exceeds 1 at the level of significance alpha equal to 0.01. Therefore, the answer to the question is yes. There is an evidence from the sample data that the drilling machine must be serviced. Now we look at task 4.4 in page 92. A manufacturer of motorcycle batteries guarantees that his batteries will last an average 24 months with a standard deviation of 12 months. If 10 of these batteries have lifetime as follows, is the manufacturer still convinced that its motorcycle batteries have a lifetime standard deviation of 12 months? Use alpha equal to 0.05. If you look at the question again, is the manufacturer still convinced that its motorcycle batteries have a lifetime standard deviation of 12 months? Obviously, we have to test a hypothesis here, especially when we are given the level of significance alpha equal to 0.05 to perform the statistical test. The parameter of interest to be tested here, as implied in the question, is the single population standard deviation sigma. Having that idea in mind, we now recognize required information to carry out the test on sigma. Yes, we need the sample size, which is 10 in this case, and the sample standard deviation or sample variance from the data. Since we are given the raw sample data, we need to use a scientific calculator to obtain the sample standard deviation S. You can check the value of S is 6.1725, which is correct to 4 decimal places. Since we are going to test sigma, then we only have one case, which is to use a chi-square test statistic in performing this test at the level of significance alpha equal to 0.05. Now, how to formulate H0 and H1? By using the standard rule where under H0 we must have equality sign, we can write H0 as sigma equal to 12. So the manufacturer's conviction about its motorcycle batteries having a lifetime standard deviation of 12 months should be under H0. On the other hand, under the alternative hypothesis H1, the manufacturer should not be convinced that its battery's lifetime standard deviation sigma is 12, or in short, under H1, sigma is different from 12. Therefore, we have a two-sided test for this task question. How to write the decision rule then? Let's look further at the next slide. Continue with solving task 4.4. We already decided on the null hypothesis H0 and the alternative hypothesis H1, which is a two-sided alternative hypothesis. As you can see, when we test sigma equal to 12 under H0, this is equivalent to testing sigma squared equal to 12 squared, which is 144. Similarly, under H1, when we have sigma is different from 12, this is equivalent to testing sigma squared is different from 144. Consequently, the decision rule is reject H0 if chi-squared test is less than the left-sided critical value, which is chi-squared 1 minus alpha over 2 nu, or if chi-squared test is more than the right-sided critical value, which is chi-squared alpha over 2 nu. As we test at alpha equal to 0.05 and the degrees of freedom nu is 10 minus 1, which is 9, the left-sided critical value is then chi-squared 0.9759 given by 2.7004, and the right-sided critical value is chi-squared 0.0259 given by 19.0228. You may want to check these two critical values, which can be obtained from Table 6 in Statistical Table Booklet, pages 36 and 37. Next is to calculate the chi-squared test statistic given by 10 minus 1 times 6.1725 squared divided by 12 squared, which is 144, which gives us the chi-squared test value to be 2.3813. The next step is to make a decision. Here, the chi-squared test, which is 2.3813, is smaller than the left-sided critical value 2.7004, which indicates that the chi-squared test statistic falls in the critical region on the left. Therefore, we can decide to reject the null hypothesis H0. What does it mean when we reject H0? It means we reject the manufacturer's conviction about its motorcycle batteries, right? Therefore, we can conclude that we do have evidence from the sample data at alpha equal to 0.05 level of significance that sigma is different from 12. Hence, the manufacturer should not still be convinced that his motorcycle batteries have a lifetime standard deviation of 12 months. Before we end this topic, as usual, let us do a checklist on this topic's learning objectives. At the end of learning this topic through this video, are you now able to attain the first learning objective, which is to perform a hypothesis test on a single population variance sigma squared or on a population standard deviation sigma using the correct procedure step by step? Remember, the testing procedure for testing either sigma squared or sigma is exactly the same. The only difference may be on writing the statement under the null and alternative hypothesis, which should either be on sigma squared or on sigma, depending on the parameter you are interested in testing. Next, are you now able to achieve the second objective, which is to identify the suitable test statistic and to calculate its value correctly? For testing sigma squared or sigma, we only use a chi-squared test statistic as the chosen test statistic. Please, we do not use a z-test, a t-test, or even an f-test for testing a single population variance or standard deviation. Next, are you now able to attain the third learning objective, that is to make a statistical decision correctly whether to reject the null hypothesis or not? In doing this, you must write down the decision rule correctly, which should tally with the statement under the alternative hypothesis H1. By comparing the chosen and calculated test statistic value with the corresponding critical value, you should be able to make a correct decision on whether you should reject H0 or remain with H0, that is, do not or fail to reject H0. Finally, are you now able to provide a sound and practical conclusion about sigma squared or sigma that you have tested? At this stage, you must answer the question in layman terms, implying what you mean by rejecting or not rejecting H0. I really hope you are able to achieve all these topics' learning objectives, which are rather straightforward. We'll see again in the upcoming videos on testing other population parameters covered under Chapter 4. Until then, Assalamualaikum warahmatullahi wabarakatuh, and thank you for watching.